Fine-tuning a 70 billion parameter model demands hundreds of gigabytes of VRAM. This resource barrier stops most developers immediately. Low-Rank Adaptation, or LoRA, bypasses this constraint entirely. We only update a tiny fraction of the weights. This technique reduces trainable parameters by over 99%. We will build the core mechanism from linear algebra fundamentals. Understanding the decomposition is the first step to mastery. This is not just theory, it is practical resource management for large models. The core assumption driving LoRA is the low-rank hypothesis. We assume the necessary weight change, delta W, lives in a low-dimensional subspace. This means delta W is inherently redundant in its structure. We exploit this redundancy using matrix factorization techniques. Instead of learning n times m parameters, we learn n times r plus r times m. R is the rank, typically set very low, like 4 or 8. This drastically limits the total parameter count. The full weight matrix W remains frozen during the entire training process. We replace the full weight update delta W with the product of two matrices, B and A. Matrix A has dimensions r by m, where m is the output dimension. Matrix B has dimensions n by r, where n is the input dimension. The resulting delta W is n by m, matching the original weight matrix W. This structure forces the update to be low rank. The rank r determines the size of the bottleneck layer. We only train A and B, not the massive W matrix itself. This is the fundamental efficiency gain of LoRA adaptation. During the forward pass, the input vector x is multiplied by the original weight W. Simultaneously, x is multiplied by the low-rank matrices B and A. The output is W times x plus B times A times x. This additive structure is critical for the adaptation process. We perform two smaller matrix multiplications instead of one large operation. The computational overhead during training is minimal. This parallel path ensures the original knowledge stored in W is preserved completely. The base model knowledge acts as a strong regularization term. Proper initialization is crucial for stable convergence and training stability. Matrix A is typically initialized using a standard Gaussian distribution. Matrix B must be initialized strictly to zero values. Setting B to 0 ensures that delta W starts as a zero matrix initially. This means the adapted model behaves exactly like the base model W at step 0. This prevents large destabilizing gradient steps early in training. We scale the output of B times A by a factor alpha divided by R. This scaling prevents the low-rank update from dominating W. The rank parameter R is the most important hyperparameter in LoRA. A higher R allows for more expressive updates but increases memory usage. Common values range from 4 to 64, depending on the specific task complexity. The scaling factor, alpha, controls the magnitude of the adaptation effect. Alpha is often set equal to R, simplifying the scaling term to 1. If alpha is smaller than R, the adaptation is intentionally dampened. Selecting the optimal R balances performance requirements and parameter count constraints. This requires empirical validation across diverse datasets. Gradients flow only through the low-rank matrices A and B during training. The frozen matrix W receives absolutely no gradient updates. This isolation simplifies the backpropagation process significantly. For deployment, the matrices B and A are merged back into W. We calculate W plus B times A and store the resulting full matrix. This merging step eliminates the inference overhead introduced by the parallel path. The merged model is mathematically identical to the adapted model. Merging is essential for production environments. LoRA introduces specific deployment challenges that developers must address. Merging is not always feasible, especially in highly quantized models. Quantization often requires specific hardware alignment for efficient matrix multiplication. Inference latency can increase slightly if merging is skipped entirely. We must manage the key value cache size carefully during inference operations. The rank R selection remains an empirical challenge, requiring careful validation across different tasks. Understanding these trade-offs is key to successful deployment.